So eigenvalues and eigenvectors can get a wee bit more complicated in infinite dimensions, as you might guess. So I was going to look at the shift operator, which comes up in 18, and the other shift operator, which comes up in 20. So let's see. So we'll do 18 first. And so in this example, we're looking at the operator that takes a sequence by shifting forward. So here T is an operator on the sequence space. Okay, so let's see, well, what happens here? Well, if we're going to find the eigenvalues and the eigenvectors, then we're going to have an eigenvalue if we get something that looks like lambda z1, z2, etc. equals t of z1, z2, etc., which is this one. And then this sets up a bunch of equations for us. So by looking at the first coordinates, we have lambda z1 equals 0. And then from the second coordinates, we have lambda z2 equals z1. And then from the next one, lambda z3 equals z2, and so forth, right? So if we have, so the first equation tells us that either lambda is equal to 0 or z1 is equal to 0. And so if we have lambda equal to 0, then what does this look like? Well, then we are looking at the equation 0, the vector on the left, equals this one right here. So I'm just restating this equation in the case when lambda is equal to 0. And that can only be true if all the z's are equal to 0. And then that means that z is not an eigenvector, because the 0 vector is never an eigenvector. So the other possibility then is that z1 is equal to 0. But if we plug that into the next equation, then we get lambda z2 is equal to 0, which implies z2 is equal to 0, because we already ruled out the case that lambda equals 0. And continuing, we end up with every zn is equal to 0. And so again, there's no eigenvector because it gets us back to the 0 vector. So this operator has no eigenvalues. If we look at number 20, then here we're looking at the operator on the same space, which is given by backward shift. So t of z1, z2, etc. is z2, z3, etc. Okay. So again, we'll look at the same thing. So if lambda is an eigenvalue, then this is going to look like lambda z1, z2, so on and so forth. And then by matching up coordinates, we end up with lambda z1 equals z2, and lambda z2 is equal to z3, and so on and so forth. And so let's see, so if z3 is equal to lambda z2, then that means it's equal to lambda times, and for z2, we know that's lambda z1 by substituting in this, well, I guess we substituted that one in here. No, sorry, what did we do? Here. Okay. And in general, we have that lambda zk is going to be lambda to the k z1. And so then that tells us that our sequence looks like z1 times 1 lambda, lambda squared, lambda cubed, and so on and so forth. And that's it. So let's see. So what else do we have? Do we have, yeah, and that works for lambda equals 0 as well. So in the case when lambda is equal to 0, then the this side is going to be equal to 0. And at the same time, this solution right here gives us the vector 1, 0, 0, etc., which is an eigenvector with eigenvalue 0. So the moral of the story is well, T has eigenvalues of whatever you want. And the corresponding eigenvector is this z sub lambda. Okay. Now, if we were doing a more advanced course, like a course in functional analysis or something like that, then you would probably be taking into account some notion of convergence and so on and so forth. And then what we'd be looking at is examples of lambda where that corresponding sequence converges or is summable, or the squares of its entries are summed to something finite or something like that. But for now, that's all we got.